In this video, we're going to prove the conjecture that we came up with in the previous video, which is that if we have a ring, let's assume a commutative ring with unity, and I is an ideal of that ring, then I is maximal if and only if R mod I, the quotient ring, is a field. All right, so here we're going to try and prove that. And I think the approach I'm going to take is I'm going to start by proving the right to left direction first. In other words, I'm going to assume well, first of all, let's assume R is a ring. And I is an ideal of R. Let's just have that in the background the entire time. And now let's start by assuming that R mod I is a field. And then we will prove I is maximal. Okay, but how do we prove that an ideal is maximal anyway? Let's just think about that for a minute. Let's just take a sidebar here. Sidebar, Your Honor. Okay, how do we prove an ideal is maximal? Well, the definition of maximal ideal is that if I have an ideal J, some other ideal, such that I is contained in J, which is contained in R, then that J has to be either I or R. That's the definition of I being maximal. Is if I imagine some other ideal which contains I, then it has to be either I itself or the entire ring. So that's how we're going to approach this. We're going to assume we have some ideal J, and we're going to assume that it's not I, that it's bigger than I, and we're going to prove it has to be the entire ring. That'll be the approach. So let's assume J is an ideal of R, I is a subset of J, and I is not equal to J. In other words, there is some A, an element of the ring R, such that A belongs to J, but not I. And we're going to prove that this forces J to be the entire ring. So we'll show that J ends up being equal to R. Okay? So let's think about what we know here. We know that R mod I is a field. We're going to have to use that somehow. I mean, that's going to be essential to our proving that I is maximal. So how would we use the fact that R mod I is a field? Well, in order to use that fact, we need to somehow convert all this information that we have into information about R mod I. So what do we know? Since A does not belong to I, that means that the coset A plus I, also known as the congruence class of A mod I, this is a non-zero element of the quotient ring. Okay, and the reason we know it's a non-zero element is the zero element of the quotient ring is the ideal itself. A does not belong to that ideal. A is outside of it, which means it has its own coset, and that coset is not the zero element of the quotient ring. Okay, so now we're getting somewhere because we have a non-zero element of R mod I, and R mod I is a field. Since R mod I is a field, this means the class of A has a multiplicative inverse. In R mod I, which we will call the class of B. Okay, so what does that mean? That means that the class of A times the class of B is equal to the class of 1, where 1 represents the unity element of R. And now I'm going to do something kind of gutsy here. I'm going to try and convert all of this back into information about R, because ultimately we are trying to prove that I is a maximal ideal of R, which means eventually we need to get out of the quotient ring and back to thinking about the ring itself. Okay, so what does this mean? Well, just thinking about how the arithmetic on congruence classes is defined, this means the class of AB is equal to the class of 1, because the class of A times the class of B, that's defined to be the class of A times B. And what does that mean? Well, that means AB is congruent to 1 modulo the ideal I. Okay, so in other words, so there exists some x belonging to I such that AB plus x is equal to 1 as elements of the ring. That's what it means to be congruent modulo the ideal I. Okay, but then wait a minute. This element here, this x belongs to I, which is a subset of J. We assumed I was a subset of J. And this A times B here, we know that A belongs to J, and therefore any multiple of A belongs to J. So AB belongs to J, and X belongs to J, therefore the sum belongs to J, and therefore 1 belongs to J. And at this point, you should be thinking, that's the strategy. We're going to prove that 1 belongs to J, and once 1 belongs to J, it's all over. Every multiple of 1 has to belong to J, so every element of the ring has to belong to J. So let's write down what we just found out, because that was a lot to write in just a sketchy algebraic notation there. But that's the reasoning that we need to use. Okay, so since X belongs to I, which is a subset of J, and AB belongs to J, since A belonged to J, AB plus X belongs to J, so 1 belongs to J, and since J absorbs multiplication, one times R belongs to J for every R in the ring. But then that means every element of R belongs to J. And so we've now proven, because J was just any ideal that contained I, that strictly contained I, since J is any ideal strictly containing I, that means I is maximal. Yes. So that's 1/2 of the proof. So now this is proven. Okay, great. All right, so now I'm going to zoom out and we will attack the other half of the proof. Okay, so let's see if we can prove that if I is maximal, then R mod I has to be a field. Okay, let's switch colors. How about a nice blue for this one? Yes, that looks nice. All right, so now we're going to prove this direction. Assume I is maximal. We'll prove that R mod I is a field. And I chose to do the 2 parts in this order because I think that we will see some of the elements of this part of the proof over on the other half. But there's a part of this side of the argument that I found just a little bit trickier. And I think the reason is we're going to have to use at some point the fact that I is maximal. And while I'm pretty good at proving that an ideal is maximal, using the fact of an ideal being maximal, to me it seemed a little bit trickier. Okay, we'll be able to do it here, no problem, but it'll just take a little bit of work. All right, so how are we going to prove that R mod I is a field anyway? Well, the way we're going to approach that, we'll have some elements that look very familiar from this proof over here. When we said over here that R mod I was a field, we were assuming that over on this side of the proof. And how did we use that? Well, we said that any non-zero element of R mod I has a multiplicative inverse. So if I pick some brackets A, where brackets A is a class not representing the ideal itself, so non-zero in R mod I, that has to have a multiplicative inverse. So that's the thing that we're going to prove over here. We will assume that brackets A is a non-zero element of R mod I. We will show brackets A has a multiplicative inverse. In R mod I. That's the name of the game. Okay, well, because brackets A is non-zero, that is, it's not the zero class in R mod I, this means A is not congruent to 0 mod I. So in other words, A is not an element of the ideal I. Okay, and now you see this kind of setting up in such a way. I mean, it feels a lot like what was happening over here, just in a different logical order with different assumptions and different things to prove. Okay, so A does not belong to I, which means, okay, and now I'm thinking we're going to take this A, we're going to build a bigger ideal than I in R, and we're going to use the fact that that bigger ideal has to be the entire ring because I is maximal. That's how this appears to be shaping up. All right, so in other words, any ideal containing I and also containing A will have to be all of R. And this is because I is maximal. Okay, so now here's the tricky part of the proof. I'm going to propose a bigger ideal that contains I and also contains A. I'm going to define J to be the set of all X plus AR such that X is in I and R is anything in the ring. And I claim that J is an ideal of R. And also that I is contained in J and A is contained in J. Okay, let's work out those last two claims first. Okay, so my claim that I belong, or that I is a subset of J, that just follows from the fact that I could take any element of I, call it X, and I could let R be 0. So I could just nullify this term of the sum. Okay, so then that X is going to be an element of J. So any element of I also belongs to J because I can just make this term go away. And also A belongs to J because I could let R be 1 because that's an element of R, and I could let X be 0. Okay, so I can make A belong to this set as well. So this set will contain everything in I as well as A, which was not an element of I. Now at this point, I would encourage you to pause the video and see if you can prove my claim that this set here constitutes an ideal, because you have the machinery necessary to do that. I know that some of you were asking for a little bit more practice on proving that things are ideals, so this is an opportunity to try doing that. I'll go ahead and continue with the proof in the video, but you should pause it and see if you can do that part on your own. Okay, so proof J is an ideal. We already know it's non-empty because it contains A. So we need to prove the other closure properties. We need to prove J is closed under subtraction and that it absorbs multiplication. All right, so let's first assume y1 and y2 both belong to J. Okay, then I can say y1 equals x1 plus ar1 and y2 equals x2 plus ar2 for some, what do we got here? For some x1, x2 in I, r1, r2 in R. Super. All right. So then what about the difference of those? Then y1 minus y2, well, that's going to be equal to x1, and I'm doing just a couple of algebra steps all in this one step here, figuring that you can check my work. All right, I claim that y1 minus y2 will be equal to that, and this still belongs to I because I is closed under subtraction, and this, of course, is still a ring element. So this still belongs to J. So J is closed under subtraction, and it's no problem. Okay, what about absorption? Well, let's assume that y belongs to J. Okay, then y is equal to x plus ar for some x in my ideal I, R in the ring. Okay, and let's let S be some other element of the ring. Then Sy is going to equal Sx plus Sar, and then I can just rewrite that for neatness as Sx plus Ars. Okay, so now I've written this as an element of the ideal. This is in I because I absorbs multiplication, and X is in there. And this is A times a ring element. So this does belong to J. So J absorbs multiplication as well. So I think we've checked off the fact that J is an ideal. I think we're done with that now. Okay, so now back to the proof at large. I think we're nearly done here. Just have a couple more steps. All right, so why did I bother proving that J is an ideal anyway? Well, now we know J is an ideal. I is a subset of it, and A is in J. So J is not equal to I, because one thing we established at the beginning of the proof is that A does not belong to I. So J has to equal R, since I is maximal. So in other words, we got this bigger ideal, and I was maximal. That bigger ideal is going to have to be the entire ring. All right, so since J is R, we know that 1 has to belong to J. So that means there exists some x belonging to I and some r belonging to R such that x plus AR is equal to 1. Because, well, why is that? J consists of only elements of this form. So if 1 belongs to J, then that means 1 has to be in this form. But then, if I think of that in terms of congruence mod I, I've got an element of I here. That means AR is congruent to 1 mod I. So that means in terms of congruence classes, the class of AR is the same as the class of 1. And then, aha, now this is where we start to parallel that other proof again. So the class of A times the class of R is equal to the class of 1. And that means this dude, that's my multiplicative inverse of the class of A. And I did that for any non-zero element of R mod I. I showed that it has a multiplicative inverse. So that means R mod I is a field. And then I think we are done.